Thank you, Terry. Thank you, Ati. It's a great pleasure to be here. Thanks for being here. And there are actually some chairs here, so if you want to, I don't feel bad that you guys are standing there. Ati mentioned the Finnish translation of Why Nations Fail. It's here, so. So it's a great pleasure to be here, and as Terhi mentioned, I'm going to give 3 lectures this morning and early afternoon. And the first lecture is a little bit like an overview. It's going to anticipate a few of the themes that are going to be discussed in greater detail in the second and the third lectures, but also is going to frame and introduce some new ideas in the context of what I want to talk about. And all of these lectures are drawing heavily on work that I've been doing with Pasquale Restrepo, who was a PhD student at MIT and is now an assistant professor at Boston University. So let me first introduce the main theme of the lectures, and as the title of the first lecture suggests, the theme is to rethink the relationship between technology and labor demand. And in particular, I'm going to take it almost axiomatic, meaning that I'm not actually going to discuss this in great detail, that any successful society has to generate both healthy employment growth and steady and broad-based wage growth. And in economics, we have presumed, both for theoretical and empirical reasons, that technological progress is almost an automatic guarantor of that sort of prosperity. That if you have healthy technological progress, that will generate both employment growth and wage growth. And therefore, there is a very strong link between better technology and labor demand. This view has not come naturally to many people, including many leading economists, such as Keynes, at various times doubted that technological progress automatically and seamlessly will generate greater labor demand and undergird prosperity. But both historical evidence and some of the approaches that we have developed as economists have somehow made many of us not pay sufficient attention to these views. So the theme of the lectures, in some sense, is that actually that consensus may have been founded both on a somewhat partial reading of history and not completely the right conceptual framework. So, in some sense, my aim in these 3 lectures is to introduce an alternative framework for thinking about labor demand, explain why it is that the previous framework is actually faulty. And here I say something because I've used this framework for 20 years of my professional life too, so I'm being critical of myself too. Why it is that in the context of this alternative framework, nevertheless, the past has often, but not always, and the not always part is important, generated labor demand expansion during times of productivity growth, but why that is not automatic, and there are actually important institutional, organizational, and innovation-related prerequisites for a expanding labor demand to result from technological progress. And then I will also, in the process, provide a lot of data and reinterpret some of the debates about the future of work. And in particular, I will emphasize that a lot of the discussion about the future of work is actually not very well grounded in economic reasoning or empirical foundations. Specifically, a lot of the debate, especially in the popular press, is dominated by a bipolar character, where on the one hand there are alarmists that think about the future of work being very bleak because of robots, artificial intelligence, and better machines replacing humans. And on the other hand, the majority of the economists are dismissive of such concerns. And I will explain why both of these are actually incorrect. And the future of work is neither very bleak nor very good. And it really depends on actually how the changes in technology are shaped and how they interact with other things such as demographic change, which I will speak a lot in the last lecture. Perhaps one place to start, given this emphasis on productivity, is actually with a discussion of how well we are doing on productivity. Actually, it turns out that there is also a big disagreement on there. So here I'm citing somebody who is just a representative of the techno-optimism. Ray Kurzweil is the chief engineer and scientist of, or one of the chief engineers and scientists of Google, and has been writing continuously about how bright the future is. And for example, commenting on artificial intelligence, that artificial intelligence will reach human levels by around 2029, and in about 25 years it will also reach a billion-fold human capabilities, or what he also calls singularity, because we have going to have such amazing capabilities for producing anything that you want, because machines can program machines from then on. His earlier predictions were putting that at not 229, but at around the mid-220s, but he's pushed it a little bit further. This is seems a little bit overblown, but it's actually a very common view among many people in the US and some in the UK, for example, who are in the technology field. But so far, and this is part of the context and part of the puzzle, that it's not Ray Kurzweil, but my former colleague Bob Solow who is it right. In 1987, in a New York Review of Books article, he wrote, when people were getting excited about the beginning of the digital age, personal computers, that you can see the computer age everywhere, but in the productivity statistics. And everybody told Bob, you're an old-timer, you don't understand, technology is great, computers are great, just wait, it's around the corner, and then we're going to have a technological boom. But it's been more than 30 years since Bob Solow wrote that, and he's still right. So here is data from Bob Gordon on total factor productivity growth in the US, and actually this pattern is very similar in Europe. In the 1940s, 50s, actually 30s also, there was very rapid TFP growth. For those of you who, I know the majority of the people are economists here, but just briefly, for those of you who are not economists, one way of thinking about TFP is if you keep all your factors of production, the skills and physical capital the same, how much does from one year to another the GDP, gross domestic product, the total value of goods and services in the economy increase? So that's pretty remarkable. In the 50s, 60s, and 70s, you had about between 2 and 3, and in the 50s actually just over 3% increase in TFP growth, which means that if we didn't do anything else in the US economy, we were still growing about 2 or 3% a year in terms of gross domestic product. But the computer age, 1980s, 90s, 2000, 2014, including the more recent advances in robotics and information technology, those rates of growth have been much slower. A legitimate discussion is whether this is about mismeasurement. And some people have claim that, but if you look into the details, and there are many aspects of it, and I'm not going to go into details, not to be too much on a tangent, is that it's very difficult to make a case that the slowdown is only because of mismeasurement. There is mismeasurement, but it doesn't look very much like mismeasurement explains most of this slowdown. So on the productivity front, actually, the picture is a bit of a puzzle. It isn't that we are going through this amazing technology age, which is bringing a time of plenty, but it's actually in some respects more bleak. But the real bleak picture, and again, I'm going to use US data to start with. I'll show some European data as I go along. Part of the reason why I'm focusing on the US is both because of the perception, when I'll talk about whether that perception is right or not, also that US is a technological leader, but also because there are a lot of parallels, and when there aren't parallels between Europe and US, I'll highlight that. So actually, the bleak record that I pointed out becomes much, much more striking and puzzling when you look at the labor market. And I will show a number of things about the labor market in the next few slides to set the scene, but this is sort of a summary slide that really highlights the extent of the puzzle. So what I'm showing here in these two panels is the growth of the private wage bill. So this is total wage payments of the private sector in the US. You could put in the government, doesn't matter, but I just focused on private sector. So this is essentially a measure of labor demand. How much are businesses willing to pay for labor demand? And to make things a little bit tidier, I've divided it by population, but it doesn't really matter too much. On the left, you see what happened in the 4 decades following World War II. And it's a remarkable picture because it shows that, undergirding the optimism that many economists had about technology and growth, is that during those decades in which productivity was growing rapidly, TFP was growing rapidly, you also had a very rapid and steady increase in wage payments. So there are some fluctuations, but they're very tiny, and the trend is very straight. It's just like a straight line. And quantitatively, that corresponds to 2.5% a year. So normalized by population, labor demand grew at 2.5% a year. Population during this period grows about 1% a year. So this is 3.5% a year expansion in overall wage bill every year, year in and year out. But here is the puzzle. Look at 1987 onwards. First, it slows down from 2.5% to 1.5%. And then from 2000 onwards, it's completely flat. No growth in wage bill. No growth in overall labor demand in the US economy. This has got nothing to do, it's not directly a consequence of the financial crisis. That all things starts from 2000. So the years between 2000 and 2007, when the US economy was growing fine, there's still not much of expansion. And of course, this has direct implications for employment and wages, which I will show you next. This is US employment of adults. So we can go back further than 1980, but I'm just showing you the 1980 picture from 1980 to make it sharper. So from 1980 to about 2000, you have a fairly steady expansion of the employment rate of US adults. So in here I'm limiting this to those above 25 and below 54, so that these are really prime age men and women. No college going people before 25, many of them are not working because they are in college, or after 54 there is some early retirement. So these are people, they're not retiring, they shouldn't be in school, but the picture is very interesting. From 1980 to 2000, there's rapid expansion of this. Why? Women. Women are coming more into the labor force, and men are fairly constant around 92% for this age group. From 2000 onwards, from 1999, 2000, around that time, there's a very sharp inflection. Women's essentially stops, doesn't grow anymore, and men go into reverse. So US employment picture is very bleak. So people talk about low unemployment in the US. Yes, this is bouncing back a little bit from the recession, but look at the decline from 2000. That's the big picture here. Even more telling is what's going on with wages. So here what I'm doing is I'm showing the evolution of the real wages for men and women starting in 1963. So in each picture, I take 5 education groups: high school dropouts, high school graduates, workers with some college, like community colleges or associate degrees, college graduates, and graduate degrees. And then I normalize all of those in real terms to 0 in 1963, and then I trace the real wage growth divided by the consumer consumer price index. Which index you use matters a little bit, but not too much. On the right-hand side, I have the women. Now, the picture is super interesting because if you look from 1963 to about the mid-1970s, and the pattern is actually the same, you can use other data sources to go back before 1963, you have a period of what you might think as a rising tide lifts all boats. All 5 of these education groups are almost on top of each other. The same is true for women too. All 5 education groups are seeing rapid real wage growth. That's what I was sort of mentioning as a hallmark of prosperity. But sometime in early 1980s, a very different pattern emerges. Not only do you see a slowdown in this real wage growth, but you see a huge fanning out of wages. It's most apparent for men, so let me focus on men. For women, the picture is made a little bit more complicated because of the increase in labor force participation, so the composition is changing more, so you have to be a little bit more careful. But let me focus on men. So this group here, these are the college graduates. Look at what the college graduates, they've had an amazing run in the US since going back to the 1920s, 1930s. If you were a college graduate, that was a guarantee for wage growth. But from 1980 onwards, real wages for college graduates are flat. What about the college premium? Everybody talks about the college premium. Well, yes, there's a big college premium and it's increasing, but not because college graduates are earning more. It's because high school graduates are getting pummeled. So actually, this is the remarkable thing. So this is the high school graduates here. In the US, if you are a high school graduate man today, and your father was a high school graduate, then you're earning about 30% less than your father in real terms. That's a remarkable number, again, for a developed country, that you're essentially doing so much worse than your parents. Now, again, we can try to say, okay, you shouldn't use the CPI, you should use another price index that's more aggressive or less aggressive, etc. But the real wage decline of high school graduates, that's going to remain. Whether it's 30% or it becomes 20%, you could play around with that. But that's a very important set of facts, and it's of course not unrelated to all of the backlash in populism, support for Trump, and the alienation of many generations of people in the US and on this side of the Atlantic. The only group that's seeing wage growth are the postgraduates, really skilled workers. But even that group, you see, it's actually not the same rate as what it was doing before. So why is this? Well, of course, this phenomenon started in the 1980s, so it has attracted a lot of attention. And the first way that economists thought about this, including some of my early work on this, is through what we call skill-biased technological change. The idea that technologies have been biased towards skilled workers, in favor of skilled workers. So new technologies make skilled workers more productive, they're favored, they work with, they complement skilled workers more than unskilled workers. It's not a crazy idea, and it has some legs, but in fact, I'm going to show you that it is both limited in its ability to explain the data, but also the way that I think we as economists have approached it hasn't been completely fruitful. And to do that, I'm going to draw on some work that I did with David Otter and show you what's going on with the occupational distribution of employment. Because one prediction of, in fact, technology become more skill biased is that employers want more of the skilled occupations. So what does it mean for technology to be skill biased? It means that, well, the marginal product of engineers and technicians is increasing more than the marginal product of laborers and assembly workers, and the marginal product of laborers and assembly workers in turn is increasing more than the marginal product of custodians and really low-skilled food preparation workers or cleaners and so on and so forth. So one way of making sense of this, and other people have done similar things like this in the past, is to rank occupations according to how skilled they are. So that's what this does. And then see whether within industries or across the whole economy you have occupational upgrading. And so on the vertical axis I have the employment growth of that occupation. So it's normalized by the overall growth, so it's in shares, but that's just for making the three curves fit in the same graph. So this had color, and somehow the color has been lost in this figure. But this one here is for the 1980s. And this was the first decade in which economists were thinking about skill-biased technological change or the inequality patterns. And in fact, when they looked at exactly not this, but similar things, they thought that actually supported the skill-biased technological change idea. Because what this picture shows is that the more skilled the occupation, the faster its wage growth, exactly like the employers are demanding more of the skilled occupation. So here you have the technicians here, somewhere here you have engineers, you have professionals, managers, you have surgeons and nuclear physicists and etc. Those are expanding. Here are the assembly workers, machinists, crafts workers, clerks, transport workers, food preparation workers, custodians, cleaners, etc. So you see, the more skilled you are, the faster is the employment growth. But then, fast forward to the 1990s, it's this curve here, the pattern changes. In fact, what you see is a U-shaped pattern where the bottom is increasing, the top continues to increase still, but the sectors, or the occupations that are contracting are the ones in the middle of the distribution. Those are machinists, operations workers, crafts workers, assembly workers, clerical workers. Fast forward to the 2000s, where you really have this labor demand being completely flattened out, as I showed you. Now you get an even weirder pattern where the high-skill occupations are not growing. All of the growth comes from the bottom. So this, as a diagnostic, really says something is fundamentally different and perhaps fundamentally challenging in the US labor market. Now at this point, many of you might think, well, this is just the US. It's an unusual labor market. But many of the patterns I'm showing you are actually common. So what's not common is what's going on to these unskilled workers. That doesn't happen anywhere other than the UK and perhaps recently a little bit in Germany. But that's because bottom of the wage distribution in many countries, including Finland, Scandinavia, France, is protected by labor market institutions, collective bargaining, minimum wages, and so on. But the rest of the patterns are actually remarkably similar across countries. So here is the occupational changes in many European countries, and more countries can be included here, but those are for which we have the better data. And what you see is that the same occupations are disappearing everywhere. Clerical workers, crafts, trade, operations, assemblies. And the big expansion in many places is coming from these elementary occupations: cleaning, custodial, food preparation, sales, services, and some from the high end of this. So this U-shaped pattern is actually very common across countries. So what's going on? What's going on around the world? What's going on in the US? What's the relationship between productivity and growth? So how do we think about this? So what I'm going to argue is that in order to think about this, we need to first have the right conceptual framework. And the right conceptual framework, in some sense, has to start with what it is that the production process involves. Most of the time, in economics, we black box the production process into a production function, and that's very, very useful. But for understanding these patterns, I will submit that we need to go one step more micro-founded or microstructure and think about what underlies those production functions. And I will say one way of doing that is to think about tasks. So if you think about how is it that I get to consume a piece of garment like this? Well, there is a series of tasks that need to be completed for this piece of garment to actually reach me. First, somebody needs to design it. That's one task. Then, out of yarn, you need to you need to produce yarn. Then out of the yarn, you need to weave things into it, and then you need to color it. You need to process it. You need to use various sort of chemicals in order to be able to get to the right type of material. Then all of these production tasks need to be complemented by non-production tasks. There needs to be back office functions, accounting. Then there needs to be some sort of planning about where these things are going to be delivered. So there's a transport set of tasks. Then there is the retail and wholesale tasks. And then finally, this piece of garment can be completed. So an important set of decisions are about how to perform these tasks and to what quality. And critical in this process is which factors are those tasks allocated. For example, the spinning and the weaving and the chemical drawing and the use of chemicals and the processing, are these going to be done in a labor-intensive fashion or essentially with machines? So there were not exactly this, but there were similar pieces of garments produced, as far back as the 18th century. But many of these were actually produced essentially by skilled artisans. A very important part of technological progress that was at the root of the British Industrial Revolution was that these labor-intensive textile processes started being mechanized. So that was the big mechanization of spinning and then weaving and then spinning again and then weaving. And then from the textile industry, it spread to others like the metal works and transport and then throughout the whole manufacturing process in Britain and then in the rest of the world. That is a very different type of technological progress, as I will explain in a second. But it's not unique to textile. So if you look at agriculture, the big agricultural revolution was really about mechanization of agriculture. Horse-powered reapers, then harvesters, then combine harvesters, threshing machines, then tractors. Now tractors that use GPS and are much more high tech, and then finally now farms are actually being robotized. So all of those are about changing which factors which factors are used for producing various different tasks. A lot of the process that started with what people call the second industrial revolution with machine tools is also about substitution of machines for labor. And of course, as I mentioned, industrial robotics, automating remaining labor-intensive tasks is a very important process. But robots are not a break with the past. Before robots came, and I'll talk a lot about robots in the next lecture this morning, but before robots came, you had numerically controlled machines, computerized control machines, which were doing essentially what the robots are doing. And then, of course, the AI that I started with from the Ray Kurzweil quote is a continuation of this sort of process. So in other words, perhaps, or more than perhaps, I will try to argue, this process here is related to this. So this is a car factory floor, and what you see is that there are no production workers here. So 30 years ago, there will be a lot of people here along the production line doing the attaching, assembly, welding, painting, and all sorts of other jobs that are necessary for the body of the car to be completed, and other parts for the motor and other components of the car. But now these are automated, robotic, reprogrammable arms that are performing these tasks. There are still workers here, but most of the workers are actually non-production workers. They do troubleshooting, they do programming, they do some of the tasks related to production, but a lot of the production tasks are actually performed by robots. Now, with this background, and what I'm doing is, of course, I'm trying to paint a picture, but the picture I'm painting is that we have to think about tasks, how tasks are allocated, so the allocation of tasks to factors, and the replacement of labor in the process when you find machines that are performing now tasks that were previously performed by labor. Well, if these are really the things that we have to come to grips with, how does our existing framework deal with it? So let me spend 1 minute on our existing framework. So our existing framework essentially, as I pointed out already, posits a production function. For example, focusing on capital and labor, we would say that output, then this could be aggregate output or textiles or the production function of a firm, is a function of capital and labor, and technology comes in this special form which we call factor augmenting. AL is labor augmenting, AK is capital augmenting. And anybody who has taken a graduate growth course, for example, will know that everything is about this labor augmenting term, because once you put the labor augmenting, things work out very nicely. We can make sense of a number of quasi-regularities in the data. Things become very tractable and neat. So this factor augmenting technological change is second nature to economists. And when labor economists, starting with Feinis-Welch, Bound and Johnson, but really building on work by Tinbergen, really first started thinking about the issue of skill-biased technological change. They also use this framework. So instead of K, you put an H here, high-skilled workers, and instead of AK, you have an AH, and then you think of AH growing faster than AL as skill-biased technological change. But there are a number of problems with this approach. One problem, which the usual economics methodology sometimes underplays, is that it's not a good description. Descriptively, it's not realistic. This is not how production takes place. So, and I will try to highlight that in the next 2 slides, but essentially this type of technological progress means that labor is uniformly becoming more productive, or skilled workers are becoming uniformly more productive in all tasks. But if in fact the reality, as I've described, is that a lot of what goes on in terms of the technological progress is this substitution of new machines for labor, then this really doesn't correspond to what's going on. So the Friedmanite research methodology says, well, don't worry about that. Don't worry about realism. Well, just care about some predictions. Well, that's not a meaningful statement. Which predictions? When you change the predictions, then your framework should change, and in a way that's not very natural. And I think also descriptive realism is important for the right bridge between theory and empirics to be formed. So I think descriptive realism is actually quite critical, and poo-pooing it has been a big mistake of some economists' methodology. But more importantly, what this doesn't really enable us is to make sense of this. There's no way you can really make sense of this type of changes in occupational distribution. So even if all you cared about was the outcome, the predictions, we can't really make sense of this type of changes. And if these are really important, then this framework's not going to work. But there's a more fundamental implications coming back to where we started. Technology and prosperity and labor demand. One implication of this type of technology, or this way of approaching technology, is that when you have technological progress, it always benefits labor. It may create inequality, but it's not possible that I become poorer because Ellie is becoming more productive. So if capital becomes more productive, I become richer. If labor becomes more productive, I become richer because I'm part of the labor. If skilled workers become more productive, I should still become richer. So one prediction of this way of approaching the data, or this conceptual framework, is that this should never happen. That this is 50% or so, more than 50% of the US labor force, or men, US men, is actually losing their real wages. That's something that you can just not make sense with this model. So therefore, we really need to leave this model aside and start with something that takes this task and replacement of new machines for tasks that were previously performed by labor seriously. And the first person to develop a model like that was Yossi Zeira in 1998, but with some important differences. And so what I'm going to do is I'm going to draw on work that I've done with David Otter and Restrepo, which is the framework which I think is quite helpful for thinking about these things. So I'm going to show you today only two equations, or well, three or four equations. Okay, not many more. Okay, but this is the most important one. This slide is the most important equation slide. And in fact, even though there's an equation here, what I want to say is quite intuitive. So equations will help us, but are not critical. So this is a formalization of what I just said. Take Y, and this could be a sector, it could be the whole economy. So you want to produce this output of garment. So to do that, you need to combine tasks. So YZ is the output of task Z. Okay? So design, spinning, weaving, carding, drawing, processing, coloring, all of the non-production tasks, each one of them is a different YZ. I make it a continuum for simplicity, and I normalize this continuum to 1, and for reasons you will be clear, it goes from n minus 1 to n. Sigma minus 1 over sigma, so these tasks are combined through a CES aggregator, constant elasticity. Why? Well, it just makes it easy and concrete. But the important thing is that you need to perform all of these tasks. Not all of the tasks need to be done to the same degree. You know, you can produce garments with bad design, you can produce garments with beautiful design. So you can substitute design for other things. Some of the garments that have good design might have bad quality in terms of their stitching. So there is some substitution between tasks, and that sigma captures that. Now the key is this equation, really. This says that YZ, meaning the task Z, can be performed either by capital and labor. In particular, let me order these tasks like this, from n minus 1 to n. And let me suppose that those tasks above some threshold I, those that go between I and n, they have not been technologically automated. Which means that at the moment we don't have a way of machines performing these tasks. So if you were in the US, in the UK economy, in the British economy, in 1750, there was no way for spinning or weaving to be done by machines. It was only for another 40 years of improvements, and then spinning jenny and better weaving machines, etc., started achieving that towards the end of the 18th century. So those tasks have to be performed by labor. So what is this? You allocate some amount of labor, so LZ is the amount of labor you allocate. Now labor has some productivity in task C, gamma LZ. So it doesn't mean that spinning and weaving are different tasks. We may be as humans better at weaving than spinning. And then AL, I'm still allowing this factor augmenting technological change, both because why not? But more importantly, because I want to contrast it with the automation and new tasks as the more important drivers of technological progress. So these are tasks between I and n. So tasks between n minus 1 and I, on the other hand, have been technologically automated. So what that means is that they can be produced with labor or they can be produced with capital. And in fact, once a task has been automated, capital and labor are perfect substitutes. That's not important. They could just be very highly substitutable. But here I've just taken them to be perfect substitutes. So what this says is that I can allocate some capital, and capital has some productivity. Some tasks are really hard for capital. So for instance, as I said, farming is being robotized now. You know, some tasks are very hard. So picking strawberries seems to be actually feasible. It's hard, but it's feasible. But then their citrus fruits are harder. So that sort of captures some aspects. And then there is some productivity of AK. So you could use labor, but you can as well use capital. So if capital is cheaper, and let me focus on that case, then it's going to be more profitable for firms to use capital. So then I keep on going back instead of forward. So then this is going to be the allocation of tasks to factors. These tasks are allocated to capital, these tasks are allocated to labor. Now, here, I is the threshold for automation. I'm going to come to N in a second. So when you increase I, what are you doing? So you're increasing I from I to I prime, then you're expanding the set of tasks that capital can perform. So some of the tasks that were previously not feasible for capital to perform, I didn't have the spinning jenny, I didn't have the robots to do the welding task, so I had labor do it. Now I work out a way, new technological innovation, so I can automate these tasks. So that expands the set of tasks performed by labor, but at the same time, it displaces labor from these tasks. So labor is no longer producing these tasks. So what happens to the workers that were previously performing these tasks? Well, they could become unemployed, so that's why technology could create unemployment. We'll talk a little bit about that. But most of them actually are going to get squeezed into the tasks that were previously being performed by other workers. So there's going to be a narrower set of tasks in which labor is going to specialize because more is being taken by capital. And we'll see that the implications of this for wages, productivity, etc., are very different than this. So in particular, these examples here, spinning machines, weaving machines, horse reapers, machine tools, industrial robotics, they are all examples of this. But if the history of technology was the history of automation and nothing else, that would be counterfactual too. That would be counterfactual because what we would see is that as we make more and more progress, labor does a narrower and narrower set of tasks. And moreover, as we'll see in a second, it also implies that labor's share of value added will go down and down and down. But throughout history, we don't see that. There's a range of tasks that labor performs is not getting narrower and narrower, or hasn't gotten narrower and narrower for the last 250 years. And the labor share of value added, meaning how much of GDP goes to labor or how much the value added of an industry goes to labor, is typically quite constant or doesn't trend down. Why is that? Well, one reason, is related to this N. So when I increase N here, what I'm doing is that I'm adding new tasks. And in particular, I'm adding new tasks in which labor has a comparative advantage. So again, think of this garment. If instead of this, you look at a piece of textile being produced in the middle of the 18th century, the differences isn't just that spinning and weaving was done by humans, but design wasn't important. So, there were some very basic designs. Nobody came up with designs, and the job of the textile factory was just to stitch things together, or textile craftspeople. So, whereas if today you look at many of the firms in the textile industry, the very large fraction of their value added comes from design. So design becoming a key component of value generation in textile is the addition of a task that did not exist before. Another example. Today, if you go to factories, as I showed you here, what are these workers doing? Well, some of these workers are doing programming in the car factory. Some of the workers are doing troubleshooting, and many of the workers you don't see here, they're doing back office accounting, planning, marketing tasks. Go to a factory in the 19th century, none of these workers existed. These are completely new tasks that started coming up with first the non-production workers emerging in manufacturing at the beginning of the 20th century, and then technology-intensive tasks such as programming, electronics control, and other sort of design tasks entering into the production of manufacturing goods. So all of these corresponds to new activities that did not exist. And these new activities are important sources of labor demand, but also important sources of value, because a lot of the value of a car, like a Mercedes or a Tesla, actually comes from the design and a lot of the features that have been programmed and added to it, not just the ability that the wheels turn. So that's this n here increasing. So n goes from n to n prime, so that we're adding new tasks. And so now, therefore, we have three types of technological changes. We have AL and AK factor augmenting, we have automation, and we have new tasks. So let's now try to understand what this does. So, okay, one more equation. So you can solve this model. I'm not going to bore you with solving it. And when you solve it, you can rewrite it in this form. And to some of you, this will look like a familiar constant elasticity of substitution production function, with two differences. One is that this wasn't assumed, this is derived from the task structure. But more importantly, there are these blue terms here. These blue terms are essentially about the allocation of tasks to factors. They capture two things. The first, that productivity is going to depend on which tasks are performed by which workers. So when I add new tasks here, I'm going to have a productivity boost because that reorganization of the addition of the new tasks. But also, when I change these n-1, or sorry, n and I, I'm making capital more or less important in the production function, because these share, what are called sometimes distribution or share parameters, is endogenously changing. Now, one way of seeing that, and in fact why these are very different from factor augmenting technological change, is to look at the share of labor in value added. And again, this is going to be as I've emphasized this already, this is a key concept, and it's going to be a key concept when I next turn to the data. So let me denote that by SL. So SL is how much of value added goes to labor. The rest, in this instance, goes to machines or to capital. So you can write that in this form. So first, the orange terms. The orange terms are what you would get if you started with a standard CES production function or any other production function. This is where factor augmenting technologies come in. So let's think about what factor augmenting technologies do and what they mean in this framework. First of all, again, emphasizing descriptive realism or lack thereof, what factor augmenting technologies correspond to here is that they make labor, let's say, or capital, more productive in all tasks. So it's not that you're introducing a piece of machinery that makes this particular activity better. It makes labor better in everything. So why does then that affect the labor share? Well, the reason why it affects labor share, and this is where these orange terms come in, is that when you make labor more productive, what happens is that the allocation of tasks to labor doesn't change. So these tasks are produced with labor, these tasks are produced with capital. But what happens is that because labor now is effectively cheaper, or I can produce more of the labor services, I can produce more of the tasks in which labor specializes. So there's a substitution between tasks created by capital and labor. So the only reason why this affects labor demand is through this substitution. It's actually a very weird channel. And the only reason we are stuck with it is because that's the only way we thought about it. And you can see that it's weird that everything depends on this elasticity of substitution. So change this sigma elasticity between one from the left to the right of one, you get completely the opposite results from making labor more productive. And we always thought, oh, isn't that an interesting thing? But it's actually a weird thing. Okay? So now think of what automation does descriptively. Automation is not about increasing the amount of services of some tasks and substituting them for others. It's really about reallocating tasks between factors. So that's why those are captured with this blue term here, gamma and I. And it's completely separate. That's what I want. That's the reason why I'm imposing this equation on you, is to emphasize that it's almost like an orthogonal dimension of technology. This is what is there in our textbooks, but this is quite different and completely separable from it. So here, this has a direct effect on the labor share and labor demand. In particular, this gamma and I, you can think of this if you want as n minus I. Under some special circumstances, for example, if sigma is equal to 1, this becomes n minus I. But typically, but generally, it's increasing in n and decreasing in I. So if I change I, for example, I increase I, and I'm automating things, that directly reduces this gamma and I, and it directly reduces the labor share regardless of the elasticity of substitution. Why? Well, again, descriptively, realistically, because you're taking some tasks away from labor and giving them to capital. So that makes production more capital intensive. It increases the value added share of labor. Likewise, if I increase n, the opposite will happen. So now in this light, let's look at the comparative statics, which is what happens to labor demand. So I'm going to do this first as an equation, and then I will summarize it in words. So let me look at what happens to labor demand. And again, as in the second slide of the talk, or the third slide of the talk, I'm going to measure labor demand by wage times labor employment. So let me look at the derivative of that when I change I. Well, it turns out that you can decompose that into two effects. That's equal to a productivity effect, which is how much output changes, and everything here is proportional log. And then a second effect, which I'm going to call a displacement effect. So if the displacement effect, the blue effect, wasn't there, labor demand would increase proportionately to productivity. So the share of labor would be constant. So, but the displacement effect is always negative. Why? Because displacement effect, is this. I'm always taking away tasks from labor, or it's always this. Okay? So the displacement effect is always negative, which means that without any further assumptions, and as a first order implications, which I'm going to make use in a second when looking back at the data, labor share of value added always goes down. What happens to overall labor demand? Overall labor demand doesn't necessarily go down, even though there is this displacement effect, because there's also a productivity effect. So where does the productivity effect come from? Well, again, in the standard framework, and this actually is another very important implication, but also shortcoming of the standard framework. The way that we think of productivity is always that labor becomes more productive, or capital becomes more productive. But actually, productivity effect is broader than that. So here, productivity effect doesn't come because labor is becoming more productive or capital is becoming more productive, but because you're substituting capital for labor, and when you find it profitable to do so under some circumstances, that means that capital is cheaper, so you're gaining productivity because you're reducing your costs. So in fact, mathematically, this is what it looks like. Productivity effect is exactly equal to the difference between the effective cost of capital and labor. So the productivity effect is nothing other than the cost savings that you score because you're substituting cheaper capital for more expensive labor. That was a big deal during the British Industrial Revolution. That's what got us started on this path. But it is very different than, oh, suddenly labor has become more productive. It's a very different kind of machine. It's a very different kind of object. And one important implication of that, which I think is perhaps the place where you start seeing the value of this framework most clearly, is that going back to the productivity slowdown, you could have a lot of new technologies, and some of them very fancy and widgety, but the productivity gains might be small. Why? Because the productivity gains are about this. So if it happens that labor effectively isn't very expensive in the tasks in which you are now automating and replacing it, meaning that this term here is similar to this term, then you will have productivity gains, but they're going to be small. That's what I'm going to call so-so technologies, meaning that they are okay, but they're not great. If you want a concrete example, think of customer service, automated customer service. So 20 years ago, there were, hundreds of thousands of workers in the US economy doing customer service. And today, many, many fewer of them. Why? Because a lot of the customer service has been automated. But actually, customer service is a very complex task. It involves problem solving, a variety of millions of different questions that can be asked to a customer service representative. And machines are, frankly, not very good at it. That's why everybody's nightmare is that you call an airline and then you end up with an automated system, or a bank, and then for the 45 minutes you try to explain what your problem is and doesn't understand, and finally you're connected to a human. So that's a so-so technology. It has replaced people, but it hasn't really improved productivity or reduced costs all that much. So that's all about this term. Summary. Effect of automation on labor demand is a productivity effect plus a displacement effect. Displacement effect is always negative, productivity effect is positive. But because of the displacement effect being negative, labor share always goes down. And because this productivity effect, because of this so-so technology, can be small, the overall impact of automation on labor demand can be negative. So therefore, three differences from the basic framework. Descriptively, technological change has a very different impact. Second, labor share always goes down as a result of automation. That doesn't depend on elasticity of substitution. And in fact, realistically, you can get very large changes in labor share, as we'll see in a second. And third, contrary to the standard framework, productivity growth can go hand in hand with lower labor demand, lower wages, lower employment. But when you look at the effects of new tasks, that's the opposite. So let me not give you the equations, but it's exactly the same idea. Let me give you the summary. The effect of new tasks is again a productivity effect, but now instead of a displacement effect, you have a reinstatement effect. Why? Well, let's again look at our picture here. Displacement effect, we are taking labor out. Here we are adding tasks in which labor is, so labor is going to get reinstated. So therefore here, productivity effect and the reinstatement effect go hand in hand. They go in the same direction. Implication, new tasks always increase the labor share. Moreover, therefore, new tasks always increase labor demand for both the productivity effect and the reinstatement effect working together. But also, new tasks could be very important for productivity. Why? Because they are adding new tasks in which productivity could be very high and could actually enable a reorganization of production in a more efficient, rational way. All right, so what are you going to make out of this framework? Well, frameworks are useful for thinking about the world, and if this framework enables you to think about the world a little bit differently, that's useful. But I will also show you that you can look at data differently and actually measure these objects. And a lot of what I'm going to do in the remaining 15 minutes today, but also this afternoon, well, actually, not this morning, second lecture this morning and this afternoon is going to be about that. Well, this is just showing that factor augmenting technologies work very differently. And let me not show you the equations, since time is short. Let me give you the non-equation version. I think I've imposed enough equations on you. But essentially, using this framework, what I can do is now let me embed this in a multi-sector world. So there are many, many, many different sectors. Each sector has these potentially factor augmenting changes, as well as automation and new tasks. And then let's say, how does overall labor demand change? And you can exactly, this is an interesting exact decomposition that actually I didn't know this before I started doing this work. And it's a very, very useful decomposition. And you can decompose overall change in labor demand into 4 terms. The first is the productivity effect. You saw this productivity effect that I showed you here and here. That's happening in every sector for a variety of reasons, also because of changes in factor augmenting technologies. So you just sum those up, and that's the productivity effect. The second is a composition effect. So a lot of economic research nowadays, well, starting from Baumol's classic work on the cost disease, is about composition effects. Some sector goes up, some sector goes down. Could be demand linkages, could be technology. Those sectoral transformations are very important. Economic development is a lot about sectoral transformations. So those are going to create a lot of composition effects. So it might well be that, one sector goes down, manufacturing goes down, services go up, and that creates a big composition effect in favor or against labor. So those are going to be all in this composition effect. Then there are the substitution effects. What are substitution effects? Well, substitution effects are these things here, these orange terms here. Either because of the labor or the capital prices changing, or because of the AL and AK changing, the intensity with which I produce some tasks changes relative to others. Now, the nice thing here for that shows these all come in the same way. R and AK and W and AL. So those are all bunched into this substitution effect. And they're all mediated by this sigma. So the productivity effect, the productivity effect and the composition effect I can directly measure from the data, from sectoral data. This can also be done at the firm level, but I'm just going to do it at the sectoral level. Substitution effect, I can measure it once I know what the elasticity of substitution is. So what I'm going to do is I'm going to use estimates for the elasticity of substitution, and the consensus estimates all are around 0.8. Now you'll see that not much is going to happen from the substitution, and that's again a feature of this. Everything is mediated by sigma, but 1 minus sigma is a very small number. So, and if you don't like 0.8, you can choose 0.9, 0.7, 0.5, 0.4. It doesn't really make any difference. These 1 minus sigma is always going to be a relatively small effect. So not much is going to happen from these substitution effects either. And then the residual at the sectoral level is going to be this change in task content. And then change in task content here is the sum across different sectors. So for now, this change in task contents is a residually computed thing, and I'll show you how to do it differently and how it behaves in a second. All right. So now this is the decomposition. This can be computed from the data, as I said, so let's compute it. So let me first do it for the 1947 to 1987 period for the US. So this is the first left panel that I had shown you, and the gray triangles is that curve that is increasing, that series that was increasing at 2.5% a year. So now we're trying to explain why did labor demand expand so steadily and so powerfully for 4 decades in the US economy. And you see the answer. Is it the composition effect? No. Composition effect is completely trivial, even though the majority of research done by macroeconomists focuses on this. It's actually not a very important factor. And why it's not, I'll come back to it in a second. Is it the substitution effect the substitution effect, it should be in red because I was in red here, but somehow it's been a color coding problem. So it's in blue. So that's also very, very close to 0. And change in task content is also not very large. So everything is explained by the productivity effect. In fact, the productivity effect directly, you can measure it from each sectors and aggregate it up. So that explains the very steady growth in labor demand. So therefore, to a first approximation, why did labor demand expand so much? Well, it sounds a little trivial, but it's because labor productivity improved so much. But actually, that is deceptively simple, and it's actually not that simple. And the way to understand that is, yes, we are seeing this change in task content, and it's 0. And if that was the whole story, then I would have wasted your time for the previous 50 minutes talking about this substitution of capital and labor and new tasks, because those are all in this change in task content. But this is the change in task content in net, aggregated up across sectors. So the question is, why is it 0? So here is the answer. So now let me look at the displacement effect and the reinstatement effect industry by industry. And what you see is that underlying this 0 series, or series hovering around 0, you have a fairly large displacement effect, but it's being counterbalanced by a fairly large reinstatement effect. So in other words, this series here is about 0.5 a year. So if nothing else happened, labor demand would have declined by 0.5 a year. That's a huge number. But what's going on is that the blue series is also 0.5 a year. Miracle. Well, one is 0.5, the other one is 0.49, but yes, 0.5. So they are exactly counterbalancing each other. Where is this coming from in the data? These are the sectors where you see labor share declining, or labor share declining beyond what's justified by changes in factor augmenting technologies and changes in factor prices. And these are the industries in which labor share is increasing. So an equal number of sectors are, so to speak, expanding their labor share while some others are contracting their labor share, and those two are making up this fairly 0-ish change in task content. So going back to this picture, then a different way of saying why is the wage bill or labor demand growing so steadily, the answer is because A, productivity is expanding, but B, productivity is expanding in a way that doesn't eliminate labor. So that's the answer. So now, let's look at the 1987 to 2017 period. So this is the series that we're trying to explain, the gray one. Again, the composition effect is 0, substitution effect is 0. So what you see is that this gray figure has a shape similar to productivity. So one reason why this has slowed down in the 1980s and early 1990s is because productivity slowed down. But then from here on, you see productivity still is increasing. There's a fairly steady increase in productivity here and then continues. But the wage bill doesn't increase as much, so there's a decoupling between the wage bill and productivity. And that's because of this change in task content. So now you see during this period, the change in task content is fairly negative, which means that tasks are on net being allocated away from labor. Why is that? Well, let's look at the same thing. Displacement is now much faster, is about 50% faster than before. So before, this number went from 0 to about less than 15. Now it goes to more than minus 20. So it goes from 0.5 a year to 0.75 a year. So if nothing else happened during this period, automation or displacement of labor would imply 0.75 every year of decline in wage bill. It's being counterbalanced a little bit by reinstatement, but the reinstatement effect has slowed down from about 0.5 to 0.25. So it has slowed down quite a lot. So the combination of these two things means that now the task content is becoming very negative. So where is this coming from? It's coming all from manufacturing. That's very important because you hear a lot about the labor share declining, and labor share. Sometimes some of you may have seen data that suggests labor share is declining in many sectors in the U.S. economy. Well, that's actually not incorrect, but it's not completely correct either. So here is the labor share in the U.S. economy. And what you see is that I've created some broad sectors, so services here, all of the services I put here. Look at the services. In aggregate, some of them have higher labor share, some of them have lower labor share, but overall this is. The important thing here is that to do this in value added. Sometimes people show you the labor share in revenue. That's wrong. That's a meaningless concept because the share of intermediates is increasing during this period. That's a first order mistake. So it's very imperative that when you talk about labor share for anything that you care about, it has to be in value added. So a share of value added in services is fairly constant. But look at manufacturing. It's a huge decline. So the decline in labor share, even though manufacturing is a small sector of the economy, it's really the driver of the decline in the labor share. And this also explains why composition effects are small. Composition effects are driven by the differences in the labor share of the expanding and contracting sectors. Services are expanding, manufacturing is contracting, but by this point the labor share of the two is more or less equal. So that's why you're not getting much of a composition effect. All right, so at this point you might say, well, this is all, a little bit black boxy. So do these displacement effects really correspond to automation and new tasks or reinstatement effects? And the answer is yes, and that's what I'm going to talk about much more in the next lecture. But just to give you a little bit of a preview, since I've done this, so let's take these cross-sector measures of task content and look at their relationship with measures of automation. So here, let me focus on this one and this one. This is robots, which I'm going to talk a lot about. So the sectors where you see the decline in the labor share and the displacement effect, as I estimated, are also the sectors where you have most robots introduced. Automotives, petroleum, chemicals, plastics, electronics. And this is now going back to the 4-digit manufacturing level, and these are the sectors that are introducing general automation technologies. The more automation technologies you introduce, the more is the negative is your change in task content. What about new tasks? So we construct a variety of measures of new tasks, and let me not go into the details because my time is short. If I have time about this, I will talk about it in the second lecture, but essentially they correspond to what I described. New occupations or new occupational activities or new contents of occupations at the industry level. So we go through a variety of sources and we try to code this, but in all of these you see that the more new tasks you have in an industry, the more the task content shifts in favor of labor, exactly like what we have anticipated it. So the last thing I want to show on the data front, and then I will conclude, is that when you look at these two pictures that I showed you so far, steady growth until the mid-1980s, and then the picture changes, one reaction you might have is, oh, well, that's because we are going through a period of automation, and that's what's special about it. Well, what I want to claim, and this is going to frame a lot of the discussion, is that what is special about the last 2-3 decades is not that it's a period of automation. It is that it is a period of automation in which we are failing to do the counterbalancing things. And to show you that, I'm going to do exactly the same thing, but now for the period of the mechanization of agriculture. So this is from 1850 to 1910. In 1850 in the US economy or the UK economy, close to 75% of the labor force was in agriculture, and then slowly it left agriculture because of mechanization. So you can see that, for example, here, look at the share of labor share of agriculture. It was low to start with, but then it went down quite sharply. But observed wage bill actually continues to grow during this period. Why is that? Well, first, actually productivity growth was very fast. Big difference from today. Second, actually during that period there was a rapid reinstatement in industry. This is the period in which new industries, new occupations, new tasks. This is the time where there were no non-production workers in manufacturing floors before the 19th century, and now completely the manufacturing organization gets transformed. These are very high-skilled workers, by the way, and that's very important also. And then third, actually differently from the recent periods, the composition effect helped too. So now the composition effect is actually positive. Why is that? Well, because the agricultural sector is contracting and the industry sector is expanding, but the industry sector is much more labor intensive, so the composition effects help too. So again, there is no necessity that that periods of automation should be periods in which labor should get a beating. So what's going on? So at the end, really, I will summarize what I've said so far by saying that we cannot separate what's going on to labor to why productivity has been so slow. And at some level, productivity has been so slow, not because we are mismeasuring things, I've said that. And obviously the sort of the view of Gordon that we have run out of ideas cannot be right either, because automation, this very rapid automation, is actually a very difficult process. So we are generating a lot of innovations. So any theory that says, oh, we've run out of ideas cannot be right. But what's going on is that the technologies that we are introducing are so-so technologies. They're not getting enough productivity growth. And if they are in fact not getting enough productivity growth, you're going to have both low productivity, and two, because they are so-so technologies, the productivity effect is not going to counterbalance the displacement effect. And as a result, you're going to have labor demand not keep up with productivity, labor share going down, wages not increasing, employment falling. But why is that? Well, a lot of the work I did here, which I'm not going to have time to talk about in great detail a little bit in the last lecture, is about direction of technological change. The technologies that we choose are an outcome of the innovation. So one possibility is that perhaps we are doing the wrong kinds of innovation. So in other words, think of the economy having an innovation possibilities frontier. So you're choosing at any point in time how much of your effort to put in automation and how much of it in new tasks or other technologies that are increasing the productivity of labor, reorganizing, coming up with new tasks, new activities. It's not that innovation possibilities frontier has suddenly changed, shaped and made new tasks impossible. Possibly what's happened, and I'll provide some more insights on this later in the afternoon, we are moving along it towards more and more automation. And if that's the case, that would be a double whammy. Why? Because if you move along a concave or convex frontier, that means you're going more and more into lower productivity automation. So they are much more likely to be of the so-so kind. But also at the same time, you are completely neglecting to pick up the low-hanging fruit that gives you a lot of productivity and a lot of labor demand for labor. So the outcome of that double whammy would be bad productivity and labor suffering. So why would we be moving along this productivity frontier in this particular direction? Well, 3 reasons. 1, policy. So actually, if you think about it, a lot of the policies that we adopt subsidize capital and therefore encourage more automation and more generation of automation. Second, lack of the right type of funding, especially if creating new tasks is a more science incentive activity. And third, if the ecosystem has changed in a way, for example, because big tech companies whose business model is based on automation and eliminating labor become dominant, both in affecting academic research and the business community's priorities of innovation, that will also create an excessive force towards automation. So a variety of these combinations, and at this point it's impossible to know, but I'll give you a little bit more insights on this as we go along in the next 2 lectures. All of these will push us along the frontier, perhaps towards the wrong kinds of innovations with potentially negative implications for productivity and labor. But if it is, and that's again my emphasis on the agriculture, it's not because technology says labor is doomed, the future is impossible for labor because of technology. It's more because of the choices we make, the institutions, the education system, the innovation ecosystem that undergirds what type of technologies we do and how we use them and whether we use them efficiently or not. All right, thank you.
We have time for 1 or 2 very quick questions. So if you have any questions, please raise your hand. So Ellie will give you the microphone.
These tasks, are those for high-skill workers or low-skill workers?
Great question. That's a great question. And so the other factor that I did not talk about are these bottlenecks. And those are very important because they prevent new tasks and they prevent whatever technologies you use from being used efficiently. They are maybe institutional, they may be organizational, but importantly, they could be skill related. So many of the new tasks require skills and require different types of skills. And if the workforce is not ready in terms of its skills, then that's going to really hamper the creation, the use, and the productivity gains from these new tasks. And in fact, I think there's a lot of evidence that, and I mean, we've done some of this work, although I don't have them with me, that in fact, automation is inequality increasing. I'll talk a little bit about that. But in fact, the new tasks themselves are inequality increasing also, because they favor certain types of skills and the workforce doesn't have them. That doesn't mean that inequality has to increase because at the same time you're reorganizing production in different ways. But again, it underlies that there are more micro interactions, and I just left them out for simplicity. But that's absolutely very critical. In some sense, you want to think about an assignment model where there are some new tasks and there are heterogeneous skills, and some tasks favor some skills, and the shortage of different skills creates different types of quasi-rents. But I've left all of those things out of these presentations. Thank you for that question.
Okay, thank you.